Welcome to another module in this massive open online course on the principles of probability and random variables for wireless communications. So, in the previous module we were looking at the concept of independence and independent events. We had defined the concept, we had defined mathematically what does it mean to say that two events A and B are independent. Today let us continue to look at other examples of independence. For instance, we had looked in the previous module, so we were talking about independent events we are currently focusing on independent events, and we had looked at this particular example where we had looked at our sample space consisting of 4 PAM modulation, that is minus 3 alpha comma minus alpha, alpha and 3 alpha. We had said that this is our 4 PAM or MPAM, memory PAM pulse amplitude modulation constellation. This is our 4 PAM constellation, and we had considered the probabilities 1 by 8, 1 by 8, 1 over 4 and a half, and we had also looked at two events corresponding to the first event is A, which is the symbol minus 3 alpha or alpha, that is the symbol is either minus 3 alpha or alpha, and B, which is basically that the symbol is basically alpha. And we had realized that we had rigorously proved that the event that the symbol, that this event A where the symbol is either minus 3 alpha or alpha, and this event B where the symbol is alpha, these two events A and B are not independent. So, we had realized, so we had established in the last module that these two A comma B are not, these are not independent. Okay, so we had realized that these events A and B are not independent. Then what is, then one would like to ask, then what is the relevance of independence in communications? What is the relevance of independence in digital communications or wireless communications, right? What is the relevance of this concept of independence and independent events in a wireless communication system? The relevance is that we had looked previously at a single symbol. Remember, when we looked at the previous example, we had talked in the context of a single symbol belonging to the set A, that is the event A and event B in the context of single symbol. However, now we will start looking at the concept of different symbols generated, because we have a wireless communication systems. So, the source is generating a stream of output communication symbols, alright. So, when we look at these different symbols which are generated at successive instants of time, these different symbols in the digital communication system or the wireless communication system are frequently independent. So, what we would like to say is that the symbols generated at different the symbols generated at different time instants are independent. Alright, so the symbols that are generated at different time instants in digital communication or a wireless communication system are frequently independent. I am not saying this is always the case, but frequently the successive symbols, information symbols, or the successive digital modulation symbols that are generated by a communication system, these are frequently independent. So, let us see what this means. For example, let x1, let this denote the first symbol that is generated at time instant 1, x2, let us say x2 denotes the second symbol, then x1 comma x2 are independent. Right, we are saying that if x1 is the symbol that is generated at time instant 1 and x2 is the symbol that is generated at time instant 2, both of these can be drawn from the same digital modulation constellation. For instance, in this example, let us say x1 and x2 are both symbols that are drawn from the 4 PAM constellation, that is x1 belongs to the set minus 3 alpha, minus alpha, alpha comma 3 alpha, x2 also belongs to the same set, that is minus 3 alpha, minus alpha, alpha and 3 alpha, and we are saying that these two 4 PAM symbols x1 and x2 are drawn independently from this sample space corresponding to the Emery PAM or the 4 PAM, the 4 pulse amplitude modulation constellation. So, we are saying this x1 and x2 are symbols generated independently from the 4 PAM constellation, alright. In fact, to extend this analogy further, we can consider a source S, and frequently this is the case, that is we can consider a source, this is generating the symbols x1, x2, x3 and so on. So, the source is generating various symbols. Each xi, that is the ith symbol generated at the ith time instant, each xi is generated we say IID, which stands for independent identical identically distributed from S, which is our 4 PAM constellation, that is minus 3 alpha, minus alpha, alpha comma 3 alpha. So, what we are saying is not only x1 and x2, all of these symbols that are in communication system, it is continuously generating a stream of information symbols, right, continuously generating a stream of modulated symbols. We are saying these symbols x1, x2, x3, x4, all of these, each of these symbols xi are independent, and not only that, they are identically distributed, each is generated independently and has the identical distribution as the other, in the sense that they belong to the 4 PAM constellation, that is the set S with the symbols minus 3 alpha, minus alpha, alpha and 3 alpha, and they have the same probability distribution. So, each of these symbols are generated these are independent and identically distributed according to the 4 PAM from the 4 PAM constellation. So, these symbols are generated independent identically. Alright. Let us take a simple example to understand this. Let us look at a simple example to understand this thing. So, let us ask the question, if x1 comma x2 are if x1 and x2 are independent, what is the probability that x1 is equal to, let us ask the question, what is the probability that x1 is equal to alpha and x2 is equal to 3 alpha. So, we are saying, we are asking the following question, we are looking at a simple example, we are saying x1 and x2 are two symbols that are generated by this 4 PAM source. So, these are the two symbols that are generated by this 4 PAM source, and we are asking these, and we are given that x1 and x2 are generated independently, and we are asking the question, what is the probability that x1 is equal to alpha and x2 is equal to 3 alpha, right. So, these are generated independent and identically from our 4 PAM source. So, we are asking what is the probability x1 is equal to alpha, x2 is equal to 3 alpha, that is x1 comma x2 is equal to alpha comma 3 alpha, and this answer is as follows: the probability that x1 equals alpha comma x2 is equal to 3 alpha. And since we said that these two symbols are generated independently, now we can use the property of independent events, that is the joint probability. Probability of the intersection is the product of the individual probabilities. Therefore, this is equal to the probability x1 equals alpha times the probability x2 equals 3 alpha, and as we have given the values initially, the probability that x1 equals alpha, this is equal to 1 by 4, the probability x2 equal to 3 alpha, this is half. So, this is basically equal to 1 over 8. So, this is a simple problem where we are saying what is the probability that we have two symbols x1 and x2, and these are generated independently, and we are saying what is the probability that x1 equal to alpha and x2 equal to 3 alpha. We said the probability of this joint event is equal to the product of the probabilities, since these two symbols are independent, which is equal to 1 by 4. The probability that the product of the probabilities x1 equal to alpha and x2 is equal to 3 alpha, which is equal to 1 by 4 times half, which is equal to 1 by 8. So, this is a simple problem. Now, let us look at a slightly more refined problem to understand this better, which is, let us look at this. Let us look at this example. Consider the 4 PAM source as usual, our 4 PAM source generating IID symbols, that is independent, identically distributed symbols from the modulation, the constellation S is equal to minus 3 alpha, comma alpha, minus alpha, comma alpha, comma 3 alpha, and we said the probabilities are 1 by 8, 1 by 8, 1 by 4 and half. This is the distribution, and we consider a block of n is equal to, consider a block of n is equal to 10 symbols, that is we are considering symbols x1, x2, x3, so on until x9 and x10. So, basically we are considering a block of n is equal to, we are considering a block of n is equal to 10 symbols, and we would like to ask the following questions. What is the probability that all the symbols in the block are element of the set? So, the first question we would like to ask is, what is block belong to the set A equals minus 3 alpha comma alpha. So, the first question, so what we are saying is the following thing, understand this example. We are considering a source which is generating IID 4 PAM symbols, that is each 4 PAM symbol, that is each symbol belongs to the 4 array, TAM constellation, pulse amplitude modulation constellation, and each symbol is generated independently and it is identically distributed according to the distribution of the 4 PAM constellation that is given. And we are considering a block of 10 such symbols, that is x1, x2 until x10, where each of these symbols is generated in an IID fashion. And we are asking the question, the first question that we are asking is, what is the probability that all of these symbols, that is each of these symbols x1, x2 until x10 belongs to the set A, which is minus 3 alpha comma alpha. That is basically we are asking the question, probability that each xi belongs to the set minus 3 alpha comma alpha. Now let us first compute the probability that a given symbol xi belongs to A, that is basically the probability that a given symbol xi belongs to the set minus 3 alpha comma alpha, and this is equal to the sum of the probabilities corresponding to the symbols minus 3 alpha and alpha. This is basically equal to 1 by 8 plus 1 by 4, that is equal to 3 by 8. This is something that we have already seen. That is, what are we saying? We are saying that the probability that a given symbol xi belongs to this set A minus 3 alpha comma alpha is 1 by 4 plus 1 by 8 equals 3 by 8. Now let us ask the question, what is the probability that all the symbols belong to this, all the symbols are either that belong to this set A, that is all the symbols are either minus 3 alpha or alpha. That probability is basically the probability, we are asking the question, what is the probability that x1, x2 up to x10 belong to this set A, which is now, because these symbols are independent, which this is now basically the product of the probabilities, probability x1 element of A times the probability x2 element of A times the probability x10 belongs to A, which can now be seen to be given as this is now each of these probabilities, probability x1 belongs to A is 3 by 8 times 3 by 8, so on and so forth, the product of 3 by 8 10 times, which is equal to 3 by 8 raised to the power of 10. So therefore, we have now computed using the independence and identical distribution property, we have computed the probability that all of these symbols x1, x2 up to x10 belong to this set A, that is each of these xi's x1, x2 up to x10 is either minus 3 alpha and alpha. The probability of that is basically 3 by 8 raised to the power of 10, and we have used the independent identical distribution property of these various 4 PAM symbols to calculate that. Let us now extend this example further. Let us now ask the question, what is the probability that none of the symbols probability that none of the symbols belong to A equals now we are asking the reverse question. First we have answered the question, what is the probability that all of the symbols belong to A. Now what is the probability that none of the symbols belong to A, and this answer is also fairly straightforward. If none of the symbols belong to A, then all the symbols must belong to A complement. That is, if none of the symbols are either minus 3 alpha or alpha, it means all of the symbols should be basically either minus alpha or 3 alpha. Therefore, the probability that a given symbol does not belong to A is simply the probability that a symbol belongs to A complement, that is the probability that the symbol belongs to the set minus alpha comma 3 alpha, and this is also the probability xi belongs to A complement is 1 minus the probability, remember, is 1 minus the probability of A complement is 1 minus the probability of A, that is equal to 1 minus 3 by 8, which is equal to 5 by 8. Now we are asking the question, what is the probability that all of these x1, x2, now we are asking the question, what is the probability that all of these x1, that is none of them belong to A, which means all of them belong to A complement, which is basically, again, since x1 and x2 x10 are independent, that is simply the product of the probabilities x1 belongs to A complement times the probability x2 belongs to A complement times the probability x10 belongs to A complement, which is equal to 5 by 8 times 5 by 8 times 5 by 8 equals 5 by 8 raised to the power of 10. So, therefore, now we have answered the question, what is the probability that none of the symbols belong to A, which means all of the symbols must belong to A complement, and the probability of that is 5 by 8 raised to the power of 10. Alright. Now, let us ask another question, which is the last question, where is part C of the same question, which is basically the following thing. Let us ask the question, what is the probability that at least one of the symbols belongs to A? What is the probability that at least one of the symbols belongs to A? Alright. So, we are asking the questions that we have this block of symbols x1, x2 up to xn. What is the probability that at least one of these x1, x2, x up to x10 belongs to the set A, that is at least one of these x1, x2 up to x10 is either minus 3 alpha or alpha, that is at least, that is one of x1 comma x2 up to x10 is either minus 3 alpha, or alpha, that is at least one of x1, x2, x10 is either minus 3 alpha or alpha, and this probability is also very simple. The probability that at least one belongs to A is basically 1 minus the probability that none of them belong to A. And we have already computed in the previous part what is the probability that none of them belong to A, and therefore, the probability of at least, therefore, probability belongs to A equals 1 minus the probability that none of them belong to A, which is basically equal to 1 minus 5 by 8 raised to the power of 10, and it is very simple, right. So, we have calculated what we are saying is the probability that at least one of these symbols, in this block x1, x2 up to x10 belongs to A is basically 1 minus the probability that none of them belongs to A, and the probability that none of them belongs to A is 5 by 8 raised to the power of 10. Therefore, the probability that at least one of them belongs to A is 1 minus 5 by 8 raised to the power of 10, and that is what we have computed over here. Okay. So, what have we seen in this module? In this module, we have seen something interesting. We have seen that basically what we have seen is we have seen that concept of independence as applied to the context of digital communication systems or wireless communication systems. We have said that although the previous example we had seen that the two events were not independent. When we looked at the two different symbols, the two different symbols generated at different time instant by a communication system, these are independent, right? These are independent, and therefore one can calculate. Now given a block of this, now we have looked at an example about the various properties, that is given a block of these symbols, that is x1, x2 up to xn, that is a given a block comprising of 10 symbols. What are the various properties? What can we say about the probability that none of the symbols belongs to a certain set A? What is the probability that at least one of these symbols belongs to a certain set A? All of these exploiting basically the independent identical distributed nature of these various symbols, generated by the source, generated by the digital communication source or the source in the wireless communication system. So this is an important aspect, or this is an important key impact of, or we can say the relevance of this property of independence or independent events in the context of wireless communication systems. So we will conclude this module here. Thank you very much.